In this section, we begin with our first objective of using the ratio test to determine if a series converges or diverges. So first, let's talk about what the ratio test states. So if we have a series whose terms are not zero, the series will converge absolutely if the limit as n approaches infinity of the absolute value of a sub n plus 1 divided by a sub n is less than 1. If that limit is less than 1, then the series converges absolutely. Remember that a series that converges absolutely means the series also just converges regularly. However, the ratio tests that the series diverges if the limit, that same limit of the ratio of the terms, is greater than 1. So if that limit is greater than 1, or if that limit is equal to plus or minus infinity, then the ratio test concludes that that series will diverge. So it tells us when the series converges and when the series diverges. It does not tell us anything about the convergence or divergence of the series if that limit is equal to 1. So if that limit is equal to 1, the ratio test is inconclusive, which means we're going to need to try another test. So let's begin with example 1. I'm going to test the convergence of this series using the ratio test. First, I will observe that a sub n, the sequence on the inside of that series, is 2 to the n divided by n factorial, which is not equal to 0. We do have non-zero terms. That's a condition necessary for the ratio test to be used. I will just point out for our convenience that a sub n plus 1 means replace n with n plus 1. And so we have that expression there. Now let's take a look at the limit as n approaches infinity of the absolute value of a sub n plus 1 divided by a sub n. So this will be the limit as n approaches infinity of the absolute value of a sub n plus 1 is this expression here. And that we will divide by a sub n, which is the original expression that was on the inside of the series. So on the inside of this absolute value, we are dividing fractions. So I will simplify that by multiplying by the reciprocal. I'll also go ahead and drop the absolute value bars because everything on the inside of our series is positive, and so we do not need the bars. So I've gone ahead and flipped this one. If you're wondering, I took the denominator and the fraction in the denominator and flipped it to multiply by the reciprocal. Now let's start simplifying this expression. The 2 to the n plus 1 I will separate as a 2 to the n multiplied by 2 because that 2 does have an exponent of 1 on it. The n plus 1 factorial I will start expanding into an n plus 1 times n factorial. And I'm going to stop at the n factorial because there is the n factorial in the second numerator, and then there's the 2 to the n in the denominator. At this point, the 2 to the n's can cancel as well as the n factorials, which leaves us with the limit as n approaches infinity of 2 divided by n plus 1. And that limit is equal to 0 since the degree of the denominator is more than the degree of the numerator, which is less than 1. So since this is less than 1, we can conclude that our series converges absolutely by the ratio test because we calculated that limit and that limit came out to be less than 1. So we are reaching this conclusion of the ratio test. In example 2, I'll begin by identifying a sub n, which is everything on the inside of the series, and I'll also identify a sub n plus 1, which is what we get when we replace n with n plus 1. I will go ahead and look at the limit. I'll also mention our terms of that series are not 0 because our sum starts at 0. And yes, we will get 0 when we plug that first term in, but we'll never see 0 again. So in reality, this sum really does start at 1. So don't let that make you think that you're not able to use the ratio test, because the 0 term doesn't add anything. And once n is equal to 1, we'll see non-zero terms. So I'm going to look at the limit as n approaches infinity of the absolute value of the ratio of the terms of this series. I'm going to go ahead and put my a sub n plus 1 in the numerator. And we're going to divide this by a sub n. So I'm going to multiply by the reciprocal of a sub n. And I'm going to go ahead and start simplifying this. We can drop the absolute value bars because everything on the inside is already greater than 0. This 3 to the n here can cancel with this 3 to the n, which does leave us still with a 3 to the 1 in the denominator, so we still have that. We have a 2 to the n plus 2 in the top and a 2 to the n plus 1. The 2 to the n plus 1 can cancel, and we'll still be left with one of the 2's. So just to be clear, the algebra behind this is that blue 2 to the n plus 2 is like a 2 to the n plus 1 multiplied by a 2 to the 1. Because remember, rules of exponents say that you add those exponents. So I can cancel the 2 to the n plus 1 with the 2 to the n plus 1, which would leave me with that 2 still in the numerator. We do still have that n plus 1 there. Now the degree of the numerator matches the degree of the denominator, and so we can conclude that this limit is 2/3, which is less than 1. Therefore, this series converges absolutely by the ratio test. We will begin example 3 with the ratio test, and we start off by identifying the sequence a sub n as n raised to the nth power divided by n factorial. I'll also go ahead and point out that a sub n plus 1 will be n plus 1 raised to the nth plus 1 power divided by n plus 1 factorial. I will mention that to help us when we actually take the ratio, the n plus 1 factorial in the denominator, I will write as n plus 1 multiplied by n factorial. I will point out that these terms are not 0. They're greater than 0 since our sequence starts at 1. The terms of this series will all be positive. Now let's look at the limit as n approaches infinity of the absolute value of a sub n plus 1 divided by a sub n. So we have the limit as n approaches infinity of, here is a sub n plus 1. And this is being divided by a sub n, so I'm going to multiply by the reciprocal of a sub n. We can start canceling some things. This n factorial will cancel. This n plus 1 raised to the n plus 1 power, I'm going to expand that out a little bit to help us simplify further, because we can write that as n plus 1 to the n power multiplied by n plus 1 to the first power. So I've taken this exponent of n plus 1 and split it up into the n and the 1. And hopefully you see that I did that so that I'll be able to cancel with the n plus 1 that shows up in the denominator. So we are left with the limit as n approaches infinity of n plus 1 in the numerator to the n power divided by n in the denominator also to the n power. So the entire fraction of n plus 1 divided by n is being raised to the nth power. And this is a limit that we have seen before. We evaluated this limit a couple of times earlier in the course to get the value of E. I will mention, if you want to talk to me about that limit, just shoot me an email. This goes back to Math 271, using L'Hopital's rule to evaluate that limit. So now that we have evaluated the limit, E is greater than 1, which therefore tells us that our series that starts from 1 to infinity of n to the n divided by n factorial diverges by the ratio test, because we got a value for our limit that was larger than 1. In this case, our a sub n is negative 1 to the n divided by the square root of n, multiplied by the square root of n divided by n plus 1. These terms are non-zero. They are not all greater than 0, but they're not 0. I will go ahead and point out that the nth plus 1 term of this sequence would be negative 1 to the n plus 1 multiplied by the square root of n plus 1, all divided by n plus 1, which is n plus 2. Now, to apply the ratio test, let's look at the limit as n approaches infinity of the absolute value of the ratio of the terms of this sequence. So here is our a sub n plus 1, and we will divide this by a sub n, so I'm going to multiply by the reciprocal of a sub n. Let's simplify with this absolute value, because with the absolute value, with the negative 1 to the n, or to the n plus 1, will completely go away. And we would be left with the square root of n plus 1 in the numerator, multiplied by n plus 1. And in the denominator, we have n plus 2 multiplied by the square root of n. This is a rational expression. Let's think about the degree in the numerator and the degree in the denominator. This factor here in the numerator is giving us an n to the 1/2 multiplied by the n that shows up in the second factor. So the degree in the denominator is 3/2. And if you look at the n in the denominator and the square root in the denominator, you see that the degree in the denominator is also 3/2. To conclude that this limit is equal to 1, which tells us that the ratio test is inconclusive. It does not tell us anything about the convergence or the divergence for this series. Now, when we started example 4, you may have recognized this as an alternating series. And perhaps if you would see this problem on the midterm or a test or a quiz, you would automatically start with checking the alternating series test. You would let a sub n be everything else that was left on the inside of the series. You would need to discuss the fact that the limit as n approaches infinity of a sub n does equal 0, since the degree of the denominator is more than the degree of the numerator. And you would also need to point out that a sub n is a decreasing sequence, which it is, since the denominator is larger than the numerator. Those terms are getting smaller. Therefore, we could conclude that this series converges by the alternating series test. So remember that if you're using the ratio test and it is inconclusive, that means that you need to go and use another test. It does not tell you anything about convergence or divergence. It tells you nothing. The last test that we will discuss in this section is the root test. And the root test states that a series converges absolutely, which, mind you, does also mean that the series converges, when the limit as n approaches infinity of the nth root of the terms of that series is less than 1. Similar to the ratio test, we can conclude that the series diverges if that same limit is greater than 1, or if that same limit is equal to positive or negative infinity. As well as you might be able to guess, similar to the ratio test, the root test is inconclusive if that same limit of the nth root of the terms of that series is equal to 1. So using the root test will be particularly helpful when you have exponents of n that show up on the inside of your series. I will also take this opportunity to mention that the ratio test, the test we were using earlier, can be helpful in situations where factorials show up on the inside of your series. It may be helpful to apply the ratio test. Now back to our root test. In this case, our a sub n is e to the 2n divided by n to the n. I'm going to look at the limit as n approaches infinity of the nth root of a sub n. Now the nth root is the exact same thing as an exponent of 1 divided by n. So everything inside of the parentheses has an exponent of 1 divided by n on it. Rules of exponents tells us that we combine those exponents by multiplying. So I'm going to take the e to the 2n and multiply it by 1 over n so that the n will cancel. And in the denominator, I'm going to take the n to the n. And the exponent of n, I'm multiplying by 1 over n so that the n's will cancel. And I am left with the limit as n approaches infinity of e squared divided by n. And as n gets very large, the numerator will stay constant as e squared. So this limit is equal to 0, which is less than 1. And so we can conclude that this series converges by the root test.